For this video, I'm going to summarize the Chapter 6 entitled Network Layer. Network layer are the network applications and services on one end device can communicate with applications and services running on another end device. The protocols of the OSI model network layer specify addressing and processes that enable transport layer data to be packaged and transported. The network layer encapsulations enables data to be passed to a destination within a network or on another network with minimum overhead. For the network layer or the OSI layer 3 provides services to allow end devices to exchange data across the network. To accomplish this end-to-end transport, the network layer uses four basic processes. We have addressing end devices, encapsulation, routing, and the last one is the encapsulation. First, we have addressing end devices. It must be configured with a unique IP address for identification on the network. Then the encapsulation, the network layer encapsulates the protocol data unit or the PDU from the transport layer into a packet. The encapsulation process adds IP header information such as the IP address of the source or the sender, and the destination receiving host. Next one is the routing. The network layer provides services to direct packets to a destination host on another network. To travel to other networks, the packet must be processed by a router. The role of the router is to select the best path and direct packets toward the destination host in a process known as routing. A packet may cross many intermediary devices before reaching the destination host. Each router a packet crosses to reach the destination host, and it is called a hop. The last one is the encapsulation. When the packet arrives at the network layer of the destination host, the host checks the IP header of the packet. If the destination IP address within the header match its own IP address, the IP header is removed from the packet, and after that the packet is then encapsulated by the network layer. The resulting layer 4 PDU is passed up to the appropriate service at the transport layer. Unlike the transport layer or the OSI layer 4, which manage the data transport between the processes running on each host, network layer protocols specify the packet structure and processing used to carry the data from one host to another. Operating without regard to the data carried in each packet allows the network layer to carry packets for multiple types of communications between multiple hosts. Next, we have to differentiate the Ipv4 and the Ipv6. The first one we have Ipv4 or the Ipv4 packet header. It consists of fields containing important information about the packet. These fields contain binary numbers which are examined by the layer 3 process. The binary values of each field identify various settings of the IP packet. Protocol header diagrams, which are read left to right and top down, provide a visual to refer to when discussing protocol fields. We have the different significant fields in Ipv4 header. The first one we have the version. The version of IPv4 contains a 4-bit binary value set to 0100 that identifies this is an IP version 4 packet. Then, differentiated services are diffserv or the DS. Formerly called the type of service or the TOS field, the DS field is an 8-bit field used to determine the priority of each packet. The 6 most significant bits of the diffserv field is the differentiated service code point or the DSCP, and the last 2 bits are the explicit congestion notification or the ECN bits. And the TTL or the time to live of the Ipv4 header contains an 8-bit binary value that is used to limit the lifetime of a packet. The packet sender sets the initial TTL value, and it is decreased by 1 each time the packet is processed by a router. If the TTL field decrements to 0, the router discards the packets and sends an Internet Control Message Protocol or the ICMP time exceeded message to the source IP address. The 2 most commonly referenced fields are the source and the destination IP address. These fields identify where the packet is coming from and where it is going. The source or the sender, and the receiver. Typically, these addresses do not change while traveling from the source to the destination. The Internet Header Length or the IHL, total length, and header checksum fields are used to identify and validate the packet. We have here the limitations of IPv4. The IP address depletion. IPv4 has a limited number of a unique public IPv4 address available. Although there are approximately 4 billion IPv4 addresses, the increasing number of new IP-enabled devices, always-on connections, and the potential growth of less developed regions have increased the need for more addresses. Then the Internet routing table expansion. As the number of servers connected to the Internet increases, so too does the number of network routes. IPv4 routes consume a great deal of memory and processor resources on Internet resources or Internet routers. Then the last one is the lack of end-to-end connectivity. Network Address Translation or the NAT is a technology commonly implemented within IPv4 networks. We're now done in explaining what IPv4 is. We now proceed on IPv6. In the early 1990s, the Internet Engineering Task Force or the IETF grew concerned about the issues with IPv4 and began to look for a replacement. There are different improvements that IPv6 provides. It increases address space, improves packet handling, then eliminates the need for NAT. IPv6 address are based on 128-bit hierarchical addressing as opposed to IPv4 with 32 bits. Unlike IPv4, it is only have 32 bits. It improved packet handling. IPv6 header has been simplified with fewer fields. Then with such a large number of public IPv6 addresses, NAT between a private IPv4 addresses and a public IPv4 is not needed. For the summary of the fields of IPv4 and IPv6, for the version of IPv4 header, it always set to 0110 for IPv4. Then time to live, it is commonly referred to as hop count. Source IP address, it is identifies the IP address of the sending host. Differentiated services, it identifies the priority of each packet. For the protocol, it identifies the upper layer protocol to be used next. Then the destination IP address of the IPv4 header identifies the IP address of the recipient host. Then for the IPv6 version, it is always set to 0110. Traffic class, it classifies packets for congestion control. Flow label to suggest that all packets receive the same type of handling by IPv6 routers. Payload length, it has the size of the data portion of the packet. Next header identifies the application type to the upper layer protocol. And then the last one is the hop limit. When this value reaches 0, the sender is notified that the packet was not delivered. Now we're done in summarizing the Chapter 4, which is the network layer.